Anyone still having trouble with up to the GUI? Still? Do you zero pad? And after? Okay. Zero pad a little bit after, because sometimes the radio just shuts down. And so it's like that. Anybody else? And you? And using, what system are you using? And you? But all the rest got things to send and receive? Be able to decode packets and send a SMS or something? Yeah, you got SMS. Nobody sent me an email. I was really disappointed, I have to say. So. And somebody used my call sign to transmit, by the way. Somebody used my call sign when sending packets, which I generally don't mind, except that you shouldn't be doing this. Yeah.
How far away from core do you have to be to go ahead and pick up your packet?
You know, I don't know if the Corey station is working that well. It's a little bit flaky. It's a little bit flaky. There's lots of other, like there's in West Berkeley, there's one. Like actually, look at APRS.fi. You should see where there is one. If you from here probably transmit, you might be able to get somewhere. I'll check the Corey station again. I mean, it worked, but I'm running a weird setup there, where it's the WebSDR and 2 web browser that's pumping audio into 2 servers, and it worked, but okay, should we start? Okay, welcome to EE 123, last real lecture. Woo! It was really last real lecture, because next lecture we have another invited speaker, Balin Sieber, who's going to give a talk about software-defined radios, which is a really, really good lecture. So I really recommend everybody who's listening to actually come, because we're not going to post it online. Not going to post it online, the video. So this is really pretty much it, and then there's the midterm, and then project presentation, and then your DONE. Really. So announcements. Lab 6 due tonight, and homework due tonight. Okay? Who doesn't? Yeah. Yes. Yes. It's the end of the semester. It's been rough, yeah. Yeah, post that. Is there anybody that doesn't think that they're going to be able to finish? At least up to the GUI. That's good. You guys rock. All right. Midterm this Friday. The material covers the entire class, but we're going to focus on filter design, transform analysis of LTI systems, and there may be some lab-related material. Not all the midterm going to be about the lab. There may be some material that is going to be related to the lab. Okay, and so yes, there's apart from doing the labs that you've probably done, I don't think there's an understanding. There's not much that you can do about, except like maybe going over, just remind yourself what you've done. Okay? I think that will be worth it. If you have any conflicts, please send us an email ASAP, okay, and what your conflict is, and we'll try to accommodate as much as possible. Any questions up to that? Midterm, it's going to be the same thing, 2 hours. You end up being like angry at the end, and then like you see that the grades actually were not that bad after a while. Yeah. It's going to be good. It's going to be good. We're going to challenge you. Okay, so I posted comments on the project proposals. Some of you, I told them to talk to me because, yes, and please see me. And as soon as possible, if you need. Especially if I commented something, and if you're not doing the preferred project, and I told you to see me, really do that ASAP. Okay? I want to talk right now on the preferred project. And one important thing that I really want to stress out is keep it real. Keep it simple. Okay? Start simple. Have something that you will be able to present. And then, in the rest of the time, work on improvements. Okay? But don't aim high and have nothing to present at the end. Okay? That's will not be a good strategy. And so, get something, the simplest thing working. Okay? First. I'm not saying that this is satisfactory, but at least I want you to have something that works. So you also enjoy it. So the idea is to transmit an image with the best quality in 75 seconds. Okay? From one computer to another. If you use Lab 6, Part B, with APRS style packets and no compression that you're applying on, like no processing, you take the raw pixels and you're transmitting raw pixels. Okay? If you do that, and you're representing each pixel by 24 bits, okay? So not floats, 24 bits. Okay? Then in 75 seconds, at the rate of APRS, which is 1,200 bits per second, you can squeeze in 2,500 color pixels. Okay? 2,500 times 24 bits. Okay? So, yes, and this is bytes, not bits. Okay, so it's 75, basically 7,500 bytes. Okay, that's what you can really transmit. That's it. Okay, there is nothing else you could do with this, and so this is the minimum implementation. I've implemented over the weekend a simple kind of application that reads a file of that size, breaks it into packets, sends it, constructs it back again. In 73 seconds, it did that. Okay, so that works. It worked for me. I was able to get that. It took about 4 hours. That also required some debugging because, and that's why I sent some of the fixes for the -1. And thank you for your comments, by the way. So that should not be too difficult. Okay. Now, here are the tips. Start with simple. Okay. Have a way to take your data, take some image, break it into packets, send it, receive it, construct it, and display it. Okay. Start with that. No no fancy stuff, no modulation, no fancy stuff, just this. Okay? If you can do that, that's great. Afterwards, so start with a 50 by 50 pixels, because that's pretty much what that means. 2,500 color pixels means like a 50 by 50 image. And a 50 by 50 image, it's an icon, but it actually looks like an image. You can actually send something as meaningful. Okay, like I'll give you some picture, I'll upload some images that you'll be able to play with. So that's the most simple case. If we give you, one of the criteria there is we can give you an arbitrary sized image up to, I think, 800 by 1,200. Okay? What you need to do then, in order to fit it into this 2,500, you need to rescale it down. And you know how to resample. right? You learn how to resample signals. In 2 dimensions, you need to resample one size and resample the other one too. Okay, or you can do a 2-dimensional filter that first filters and then resamples. Okay, that's another way. Okay, so you know how to resample and downsize it basically. Okay, and then after you transfer the data, you need to upsample it back. Of course, you lose the quality because you made your image lower resolution, but that's okay. That's part of it. And you'll see that there's going to be a trade-off there. I mean, how much I'm going to resample, how much if I want to maybe compress using wavelets or DCT or finite differences or some run length encoding depending on the type of the image. Like if I have lots of zeros, right, I can encode them in one number or something like this. So if I just encode the differences and I quantize, you can come up with all sorts of ways to compress. But there's going to be a trade-off. At first downsample and then compress. I mean, there's going to be a trade-off in the image quality that you'll see. Maybe it's going to be worthwhile to compress to some point and then, to downsample to some point and then compress afterwards. Or maybe it's worthwhile to just compress and then downsample. Actually, compress and downsample doesn't make sense. But there's going to be this trade-off. So that's part of, I think, what I want you to kind of feel. Okay? So decode, resize to the original and the recorder, the decoder. After you've got something working, then improve on what you got. Now, I heard some people propose to do this really sophisticated communication stuff like QAM. Let me strongly advise against using QAM. Strongly. Unless you've taken 121, 221, digital circuits for communication or something or you've worked in the communication industry, yeah, sure, go. Do QAM, no problem. Otherwise, please don't do this. Because this requires, there's a lot of subtleties with, trying to synchronize the receiver and, follow the amplitudes. And it's just there's lots of calibration that needs to be done. And it's quite intense. I would say that is a project by itself. Okay, just doing QAM. MSK, you can very easily translate whatever you've done with FSK and just, convert that to MSK. You'll have to change the demodulator, but that's pretty much it. The decoder will be the same. So again, keep it simple. If you think about this the 3.5 kilohertz that you've got basically to transmit through the radio, that's pretty much what you have. So that's really set a limit on the rate that you can transmit. So I would say going twice as fast or maybe 2.5 as fast as APRS, it's hard to do. It's hard to beat that. Unless you do the sophisticated modulations, which please don't. Okay. So, So that's one thing. I think MFSK is okay, but I don't think it will buy you much in terms of bandwidth and bit rate. So that's another thing. Yes. Did you measure in lab 5? You measured the input filter that goes into the radio, and it was about 3.5 kilohertz wide. You can improve a little bit by, maybe compensating for some of the filter and, making sure that everything is balanced. Remember, maybe the mark in space may not have the same amplitude. So if you subtract them, they may not, have a mean that's 0. Okay, so the zero crossing could be biased a little bit. So you can try to fix that, But again, based on your time. Now, if you're a team of 3, I would say, have one person to optimize the modem, and think about good ways to optimize the modem. Have one person to optimize the encoding, and have one person optimize the decoding. Okay, so you can do what's called image processing afterwards. For example, let's say you did some, low resolution, right? Like you downsampled. How do you upsample? maybe you can upsample and enhance it a little bit so it looks better. Okay? We'll give you different types of images. Some of them are cartoon-like. Cartoon-like images can be compressed way better than non-cartoon-like images because they don't have much information in them, a lot of flat stuff. So maybe have a way to decide which one is which. Okay, so you can think about that when we give you the next few images. So all these things you can think of in terms of, especially if you're doing a group of 3. Okay, so it will be good, but at least make sure that the basic things work. You send image, you put the data in, you break it into packets, you send the data out. You don't have to actually do it in packets, right? The packet thing is just to make it easier on you. There's an overhead with packets, but you don't have to do it. But it might be more robust. Okay, so again, if you really want to go beyond and you have time, let's say that took you 3 hours, you're good. You implement the compression, everything. You're able to send beautiful images. Well, how about make the communication more reliable? Get a feedback. This packet's missing. This packet's resend. Acknowledge resend. You can think of adding on top of it. It's not signal processing, but it will kind of more like 122 material. So that's another thing. I'm just giving you some ideas of what you could be doing. But the most important thing, okay, start simple. We'll try to have the project presentation be separated into those that are doing the preferred project and those are not. And so we'll try to gather those that are doing preferred project the same day, so it's like a really nice competitive environment. And please, everyone, show up because I think it will be really nice to see what the rest of you have done. Last year, there was really creative stuff that people have done. That was really fun to watch. Any questions? Yeah.
Can you use libraries for 2D wavelets?
Yeah, you can use the libraries for 2D wavelets. Yes. Can they? Use the library. Yeah, why not? Just use. Yeah, sure. Yeah, no problem. But you might be asked when a project, what does it mean? How do you do this, right? So it's not just blindly use it. If you use it blindly, then it doesn't count. I did mention that you can do also, you can use libraries for entropy coding. So I put it on the specs. That means Huffman coding you've all learned in 70, right? So you take the coefficients and you can compress, you remove the redundancies afterwards too. So you can use that one as well. Zip, gzip, all this stuff you can actually use if you want to. Okay, it might cost you with robustness, right? When something is compressed and you make one error, maybe you won't be able to recover anything, right? So it might cost you with robustness. Okay, so that's always the trade-off. Oh, by the way, HKN is going to come the last 15 minutes of the class. We really appreciate if you can also put comments in writing, in particular about your experience in the lab. What you liked, what you didn't like, and what could be improved. We really take that seriously, and we try to do that from last year to this year, and we'll hope to do that for the next one. Okay, so today's really kind of like a summary. We're going to talk about what we've done and what you could do and what's next. So just to summarize this class, we started with something very, very basic, right? Just discrete times and signal and systems. Then we went to talk about transforms. And transforms are really tools that you learn. Now it's in your pocket. The Z transform allows you to really analyze systems very well. DTFT and DFT and the relationship between them allows you to understand what a spectrum is and how do you estimate a spectrum of a signal. We talked about time frequency. So short time Fourier transform allows you to analyze signals that are not stationary over time. And then you learned also the concepts of multi-scale decomposition. So it's also a time frequency, but a little bit more adjusted to information that we sometimes really need. Is things that change fast. We'd like to actually see how they change fast. And so we'd like better temporal resolution in some frequency range. And then maybe in the low frequencies, we don't need really to track things very rapidly because that's not how natural signals behave. And so maybe we should allocate less and be able reduce the accuracy in time, but really improve our ability to resolve the frequency of these signals, or these parts of the signals. So we talked about wavelets. We talked about also sparsity. I always kind of try to put sparsity into the mix because sparsity is really a powerful way to represent signals. Okay, that when you talk about nonlinear processing, for example, all sorts of adaptive type of denoisers or reconstruction, like in compressed sensing, you can use these sparsification of signals to be able to exploit much more. Remember when we talked about, when we used the median filter for denoising of this spiky noise, for example, compared to nothing that you could do, like it almost removes it completely, while if you use something that is low pass or some bandpass filtering or any linear filtering, nothing you can really do about this. Okay. We talked about how to analyze frequencies and what are the trade-offs in terms of the window size and how we're able to measure signals that are of different dynamic range. We use the windowed type methods. There's a whole lot more about frequency analysis in the presence of noise that we haven't covered, and all sorts of other techniques that people are using to estimate frequencies by other means. Okay, and those, when and if you take 225A, for example, you'll learn about those type of techniques. We talked about the frequency tiling and what does it mean with the Eisenberg uncertainty principle. There's always these trade-offs, right? Like there's really just this patch blanket that you kind of stretch it that way or that way, but it's really is going to have always the same size. And so there's really not a lot of way to get around this. After we developed all these tools, we went and talked about sampling, how we go and convert continuous time signals into discrete time signals and vice versa. We talked about the ideal case, but definitely we try to emphasize what happens in the non-ideal case and how you can kind of combine two types of processing. Some part in the analog domain, some part in the digital domain, so you get more benefit out of the whole thing. And so, kind of, if you ever get something about this class, is that as somebody that does signal processing, I would never ignore the other side, the analog domain, the hardware part, and understand how a system behaves and how can I maybe change it to get better performances. You saw that, I kind of try to give you that when we talked about the node port sensing with Lydia, this project, where you have to have this dialogue and to understand how you can create a better system by looking at all sides of the system. And this is kind of also what we do, for example, in the work on the MRI that we do. We change how data is created, how is acquired, how is processed to get better results. In this part, we also talked about, what does it mean to have faster rate of sampling beyond the Nyquist. If somebody tells you, I have this kind of signal, I'm sampling it, I have an 8-bit ADC, and what's the rate I need to sample? And then you say, well, how about sample the Nyquist rate? And sampling in the Nyquist rate is really good in the ideal case because you know that there's always going to be some aliasing going in. And you're always going to have other issues, for example, with the accuracy of the bits. If you have only 8 bits, that gives you quantization noise. So remember, though, that if you go for higher sampling rate, then you are gaining reduction in quantization noise, right? And we talk about that when we talked about oversampling. So oversampling often helps, okay, in terms of the filtering, in terms of your ability to get better representation. Then we did things that we, are not covered by the book, but I thought it would be really useful to talk. So we talked about 2D, we talked about tomography. Okay, these are problems that appear only in multi-dimensions, right? Tomography problem. And then we spent about 3 lectures talking about compressive sampling, kind of from a high seat. But the idea here to expose you to other ways of thinking, especially nonlinear type of processing, and how you exploit different redundancies. I mean, if you think about this, band-limited signals are a class of redundant signals, right? Because they have a limited bandwidth in their spectrum. There is some redundancy. That means that you can predict them to some extent. So there's other classes of signals. Signals that lie in a small dimensional space out of an n-dimensional space. They may look random, but they, if they lie in a small dimensional space, you can exploit that. Okay, so, all this stuff translates, and you will see that when we talk about big data, for example. There's a lot of redundancies in big data, right? You can compress it, you can reduce it. Maybe you can also reduce the amount of sensor data that you acquire a certain way, right? Data collection. I didn't tell you the story, but there was a story from World War I. They were looking at testing soldiers for, I think it was STD, some sort of STD. And they were trying to test soldiers to see if they have them, but each test took a really long time. So what they did is they pulled blood from a few soldiers together, and then they tested on it. But they did it in this particular way that if there's like 1 out of X soldiers that were actually ill, or maybe 2 out of X, then they will be able actually to infer what is who's the actual soldier, even though they pulled out the blood. Okay, so this is kind of like compressive sampling if you think about this, right? You kind of do the mix, you test on the mix, and then based on these few mixes that they do, they can go back and measure this. And this was done in 1917. Okay, compressive sampling. Okay, so there's a lot of that in the world that we're heading towards. I mean, all the sensor data coming in. I mean, how do you process this? What do you store? We as humans, right? We don't store everything that we see, and we see so much. Just walking from Corey Hall all the way to here. I capture lots of information, right? Like this video, 3D video. I capture, temperature, the sky. There's lots of motions occurring. I'm hearing stuff. I'm seeing depth. And yet, I'm not blowing up now. I didn't fill up my hard drive because my brain figures out what's important, and that's what it stores. Right? So, in systems that we'll have to build in the future, something like this will have to happen because storage is not going to be unlimited. Then, from this high topic, we went to filter design, which is actually a really useful tool that you'll see in the future, because everybody needs to design a filter. Okay, so we talked about filter design. In particular, we talked about FIRs. Okay, and then the last topic we talked about the transform analysis of LTI systems, which is really a powerful way of thinking about systems in terms of zeros and poles and how their structure is and what does it mean about group delay. And you'll see that not just in digital systems, you'll see that everywhere, optical systems, and so on and so forth. So that's pretty much it. But we also did other stuff, okay? And that stuff was kind of like additional, and this has been going on for the last 3 years. when we start introducing the labs. So what we try to give you is a way to use the information that you learn and practically apply it. So you implement a sonar, you experiment with software-defined radios, which really are the way to go in terms of communication, because implementing things in software is so much easier today than doing it in hardware. Although you'll see that as you go for the hundreds of gigahertz type of RF, for example, then hybrid systems of mixed digital and analog comes back now, because it's really hard to process things at 300 gigahertz rates if your clock rate is 3. Okay. So it kind of makes sense, right? You did get a ham license, which at least that, you got something out of the class. You got some government certificate. What I'm hoping for is that maybe this bug will catch some of you, and you'll maybe use this. And you'll see that, especially in our profession, it really helps a lot to understand everything about systems, communication, but just be able to tinker with stuff. It makes you tinker, and then you understand things better. I got to it when I was 40. I was 40. So you got plenty of time. But maybe you will at some time. If you are interested in, being active and do something about this, we just got this sweet SDR for HF that's in the ham shack. Really expensive one. Really nice one that allows you to do amazing things. So if you want to get trained on that one to be able to use it, it's really nice 100-watt transmitter. Will get you really far. So let me know, and I'll train at least one of you that will be able to train more and more. We did do real digital communication, and you can see a little bit of pain, but pain is good, makes you feel alive. I used to have I was swimming. My swimming coach used to say that pain is good, makes you feel alive. Because the only time that you don't feel pain is when, well, I think, right? I'm sure somebody will argue there. We did talk about applications, and I talked quite a bit about MR because this is what I do, and I like talking about what I do. But there's, of course, tons of applications of signal processing, and I try to give you, for example, with the node pore sensing, is where something that seemingly doesn't seem related could be somewhat. Oh, yeah, I can see where things are going. So a lot of things about research and application, and even when you try to form ideas for companies and so on and so forth, is to try to see a problem in a different way. Okay, and the tools that we gave you here, I hope that we'll be able to see this. This is not an island, though. This class is not an island. I would like to show again the slide that I gave you in the first lecture. Is when you look at this, $10 device, USB device. There's so much of the department and classes that cover each aspect of this that it just blows my mind. E&M on one side, IC, like analog IC, 140, 142. That's the tuner chip. All the devices, 130. The analog digital communication, that's the chip that does the ADC. Actually, it does the whole thing about this chip over here knows how to decode TV, so DVB-T. Okay, so inside this really, really tiny chip. There's a lot of signal processing there. Actually, you can decode like QAM and stuff. It's all built in here. Okay, so really sophisticated type of processing, which you're not using for this class. MEMS, even, right? Micromechanical devices. It's crystal, right? I mean, basically, it's mechanical resonances that occur there that affect electrical behavior, and it happens everywhere. And of course, MEMS is way more than that. 120, 123, 126, 122, all the signal and systems appear here. They appear here after you get the samples out to USB. And then all the software stuff on the other side, all the other layers. It's all kind of built into this one, just one simple device, right? It's like $10. Unbelievable how much knowledge there's there, right? So before HKN will come, can I just finish in a couple minutes? Thank you. Let me tell you a little bit what's next. Okay. So if you're interested in signal systems, there's the 120 series, right? 121, digital comm. Actually, I'm not sure when it's going to be offered, but it hasn't been offered quite. 122 is the networking layer, right? You sell what AX25 is, right? But it's way more than this. Gives you a little bit. 126, probability. This is statistics, probability. This is something that our brain are not, trained to work. This is really important type of material. 127, optimization. One of the most useful classes you've ever take. So everybody take that one. Really. Control. All the system that we kind of analyze. You can also use them not just for signal processing, but also to control control systems. Medical imaging class, I do recommend it. This one, from a signal processing point of view or signal and systems point of view, talks about the different type of imaging modalities. CT, ultrasound, nuclear medicine, and MR. Okay, all of them. Machine learning and AI is really the signal interpretation part of the processing. Right? You get some signals. How do you interpret something? Not just process them in terms of filtering and so on. Like, how do you make decisions based on them? Okay, how do you detect something? Computational photography. These are actually two classes that I recommend that are going to be offered next semester, I think, which do similar things. They use signal processing to do other fun things. If you want to take something more advanced, 225A, statistical signal processing. So this is really kind of like 123 plus 126, kind of merged together and plus plus. Okay, very useful techniques. Image processing. Tells you what you do with images, 3D geometry, and so on and so forth. Computer vision is again taking the signal processing and adding to it interpretation. But before you do interpretation, you always look for features. How do you do features? You do processing. Okay? How do you make the best features? You have to understand what signals are, how you process them to get the best features. This series is getting tougher, 226A. If you like 226, I would recommend that one. Detection estimation, okay? Statistical learning theory. That's when you start adding, statistics, randomness. How you then make decisions based on them. And last but not least, 225E is going to offer next year, and I'm going to do a shameless promotion here. MRI revolutionized diagnostic medicine. Do you really know how it's going to work? It's amazing. Amazing. It's just amazing that physics allows us to do this. It's just incredible. Thank you, world. Thank you, physics, and thank you, whatever created that allows us to look inside people by looking at signal coming from nuclei, hydrogen nuclei, not atoms, nuclei. You're going to be operating two scanners, one an animal MRI scanner, as well as a human MRI scanner when you take this class. Okay, we designed these beautiful labs that you're going to go and operate these scanners. And if you take in 120, it's enough. If you take in 123, you'll be okay. No problem. Wednesday, Paul and Sieber. And with that, I'll see you on Wednesday for bowling. Please give us as much feedback as possible. And thank you so much. It's been a pleasure.